and then you can start.
Okay.
Okay, I'll just switch off the video, Amit. Okay, and mute.
Okay, yeah.
Yeah, mute myself also.
Yes, sir. We'll start in 1 minute. Maybe.
Okay, thank you.
Okay, sir. Let's start presentation.
Okay.
So, hello, good evening, everyone, and welcome to the API webinar series organized by Applied Photonics Initiative. API is a consortium of student chapters of three prestigious professional societies like SPI, OSA, and IEEE Photonics Society. We conduct technical events like webinars, workshops, and outreach programs regularly, objective of which is to share a platform for everyone who is working or interested to work in the field of optics and photonics. Before starting the presentation, let me remind all the participants to kindly mute themselves. We will have a question answer session after the presentation where you can ask the question by typing in or just unmute and speak. Without further delay, let's welcome Dr. Amit Agrawal, Associate Research Scientist at Institute of Research in Electronics and Applied Physics at University of Maryland, College Park. He received his PhD in Electrical Engineering from University of Utah in 2008, followed by a postdoc at NIST UMD, University of Maryland. He then joined as a faculty of Syracuse University in 2011 as John E. and Patricia Breer Professor of Electrical Engineering. He has been back at NIST UMD since 2014, where his group is developing novel nanophotonic devices operating from the near IR to deep ultraviolet frequencies for providing arbitrary control over the linear and non-linear properties of light in space and time. Now I would request Dr. Agrawal to kindly begin with the presentation. You may please take over now, sir.
Okay, yeah.
Thank you.
Find the screen. Can you see my screen and can you hear me all right?
Yes, sir. Yes, sir.
Right.
Both are all right.
Okay. So thank you everyone for joining at this late hour, and thank you Tapa and Varun for the kind invitation, and thank you Arpita for this generous introduction. So I'm going to talk about some of my work that my group does here at NIST. So I'm primarily, my lab is at NIST and I'm affiliated with the University of Maryland. And I'm going to be talking about some of our work from the last couple of years in developing integrated nanophotonic interfaces to quantum systems. And so the talk will mostly be about creating interfaces that talk to, say, ions or atoms and things of that sort. Okay, so next slide. I think my slideshow is stuck. Okay, yeah, so this works. Okay, so just to give you for people who are not familiar with NIST, it is located in the suburbs of Washington, DC, around 20 kilometers, 30 kilometers away. If you've never been here, it's a beautiful campus with lakes and bunch of buildings and a lot of wildlife. And I invite you here whenever you are ever in the Washington, DC area, when we are allowed to travel. It is the official office of standard weights and measures. So NIST maintains all the standards that we use in our everyday life, from seconds, kilogram, mole, and whatnot. And it has 5 Nobel laureates that work here. So the idea of the lab, or the mission of the lab, is to conduct research that advances nation's technology infrastructure that is needed by US industry to improve their products and services. So my lab is in this building. This diagonal building is the clean room. So it's quite convenient that we have some fantastic facilities here that we leverage to do what we are to further our research. So in my group is the ultrafast nano optics group, and so here we do experimental research in looking at light matter interaction in nanoscale photonic devices and systems. So to broadly classify, I would say there are 3 main areas of research. One is more on the device perspective, where we create plasmonic metamaterial or metasurface devices for spatial, temporal, or spectral control of light. So just coming up with unique aspects through nanophotonic engineering to create such devices. And examples could include nano lasers, color filters, flat lenses, and whatnot. And while sort of creating these devices, every now and then we come up with effects that we don't understand. And that's what I have created in this category of fundamental light matter interactions, where we look at very fundamental effects such as photon drag effect or chiral phenomena at the nanoscale. And then more recently, because of this quantum revolution that we are all living through, there's an effort across NIST and across the entire US and in the world on creating quantum systems, and more importantly, creating manufacturable and portable quantum systems on a chip. And some of our work is dedicated towards creating, say, portable atomic clocks and atom traps using integrated photonics. And this will be the primary focus of my talk here. Okay. How do we engineer such light matter interactions in any of these devices or these applications that I spoke about? And our sort of playground is based on 3 different systems. The first system is purely metallic, so where we leverage propagating a localized surface plasmons to say create a laser or look at sort of catalysis is using single nanoparticles. So depending on sort of the application, we work with both localized surface plasmons and nanoparticles or propagating plasmons on flat metal dielectric interfaces. And then equivalently, we also work with metallodielectric systems where we engineer, say, example, metal insulator, metal plasmonic modes to engineer the dispersion and create volumetric media that does not have a property, say, that exists in natural medium, or by using this metal insulator, metal plasmons in a sort of a micromechanical system, we can create optical modulators. And then finally, most of the focus of our work in the last, I would say, 2 years has been on purely dielectric systems because they are CMOS compatible and we can make them using standard CMOS lithography tools in the clean room. And these include both integrated photonic devices as well as metasurface devices where we leverage propagation in geometric phase or dielectric mirror resonances to create photonic devices with multifunctional response. And again, for the purposes of my talk, this is the area where I'm going to focus most on, which is purely dielectric systems. Okay. A quick outline for my talk. I'm going to give you a introduction on what metasurfaces are and where they're important, how they work for the students in the audience. So this will be sort of a low-level introduction of metasurfaces. Then I'll talk about, I'll change gears, and then I'll talk about what is the need for chip-scale AMO systems. So these are atomic, molecular, optical systems. So mostly systems that rely on atoms and ions, and trapped atoms and ions. And then finally, I'll talk about our recent work on creating an atomic clock using nanophotonic devices. Okay. So for those of you who are not familiar with metasurfaces, they are sort of a flat counterpart of bulk optics. So these are compact, multifunctional CMOS foundry manufacturable platform for shaping light. And so now one could think of a bulk optical element that you use in your lab, such as a wave plate or a lens or a mirror or some other element that you use in your lab as something that could be made in a foundry. That's quite remarkable because now one can take these your device designs that you use in your bulk optical elements and directly make them by the thousands or tens of thousands in a foundry run. And so shown here is an example of a 12-inch wafer fabricated at advanced applied materials lab for this company called MetaLens, where each one of these lenses, this wafers consist of 5,000 lenses. If you keep zoom in, then these are 1 millimeter diameter lenses. And if you further zoom in, then you can kind of see the phase profile that one needs to focus light. And these are individual silicon nanopillars that are millions of that are in constituent of this 1 millimeter lens. Okay. So these lenses are what are going to show up in your cell phones pretty soon. So that's where the application space is, at least for MetaLens. And then more importantly, I would say from a broad perspective, they offer the potential to replace a table full of bulk optics with a single semiconductor wafer. Okay, and I'll talk about this in a second as I go through my talk. And another example that I like really well is this paper from Federico Capasso's group from Harvard, where they made 40 or so metal lenses on a single semiconductor wafer, glass wafer here, and you can see the nanopillars using deep UV lithography. And then what you see is that each of these lenses focus to a certain focal spot. Again, this kind of points towards that in a single deep UV exposure, I can make 40, 50 lenses on a wafer or thousands of lenses on a 12-inch wafer and really scale your process, right? So in my lab, we work on 3 different aspects of metasurfaces as spatial shaping to create multifunctional photonic devices that can shape light in odd ways, all the way from deep ultraviolet to visible to near IR frequencies. Part of our group is dedicated towards working on temporal shaping. I'll briefly touch on this, but this will not be the focus of my talk. And then more recently, we have been working with lithium niobate and gallium arsenide based platforms on nonlinear beam shaping, as well as doing some work on spectral engineering. Okay, so I'll briefly touch on all of these as I go through my talk, but most of my talk is going to talk about spatial shaping of light for AMO applications. Okay. How does a metasurface work? Okay, so if I now take one of these devices here, or the one shown in the middle, it consists of this nanopillar. Okay, and so in the simplest sense, this is the building block of my metasurface. Okay, so this is my unit cell, And if I propagate light through this unit cell, this high index nanopillar on a low index substrate, then what will happen is light gets guided as a waveguide. And what you would expect is that if I make this waveguide smaller in diameter, then my mode spills out more outside, and therefore the effective mode index is lower, because it sees less of this high index material. If I make this nanopillar wider or larger diameter, then most of my mode is inside this material, and therefore my mode index is higher. Okay, so now you can see that if I am in a non-resonant condition where light just comes in, propagates through this waveguide and comes out, in this non-resonant condition, by changing the diameter of this nanopillar, I can change the phase from 0 to 2 pi. So you can kind of see this wavefront that is tilted, and that as a result of each diameter of nanopillar giving you a different phase as it propagates through it. Okay, so I can look at it more mathematically. So again, if I have a nanopillar, let's say made of silicon on an SiO2 substrate of a particular height, say h here, and at some wavelength 850 nanometers. If I change the side length or the diameter, if it was a circular in shape, and I look at the phase as a function of this diameter, then what you could see is that just by changing the diameter from 60 or 70 nanometers to 150 nanometers, I can get the total full 0 to 2 pi phase shift that I need. Okay, and then all the while maintaining a transmission that is larger than 1 or close to 1. Sorry. Okay. So you want high transmission and you want a phase that gives you 0 to 2 pi. And now this numbers, they become your library. Okay. So now if I want to make any element that gives a phase to an incoming optical wavefront, then all I need is this library. Then I just pluck these nanopillars and then place them spatially. So for example, if I want to make a lens has this phase function. This is the sort of the spherical phase function for a lens, where the phase spatially is given by this equation. And so if I now just take a cross section of this lens as a function of, say, x or diameter here, and I plot the phase, then this is the phase wrapping function that this equation gives me. So if I want to make a lens out of a meta surface or these nanopillars, all I have to do is to take a pillar and put it at these dotted places. Okay, so if I need this phase, then I pluck a nanopillar and I place it here. And once we go and then lithographically make it in a 2D surface, then it will focus light. Another thing that you would notice is that for a certain diameter of these nanopillars or for a certain size of these nanopillars, the transmission actually goes to 0 or close to 0. And this is reminiscent of a resonant response. Indeed, this is the Mie resonance or the geometric Mie resonance of a nanopillar. Okay, so light stays trapped as a Fabry-Perot resonance in this pillar. So usually for applications that only require phase transformation, so you are basically just going through the nanopillar and imparting a phase shift, you want to stay away from this resonance because this is loss inducing. However, for certain applications such as, say, a color filter, where you are trying to make a color filter different colors, so by creating 3 nanopillars, for example, with different RGB and red, green, and blue resonances and placing them spatially, now you can create a beautiful painting, for example. So for certain applications, we stay away from it. For certain other applications, you want to work here, right? Okay, so it just depends on what you are trying to do. So now, okay, so I said then we can map this. Now we make them. So here is an example of a meta surface. This is 2 millimeter diameter. This is 3 millimeter diameter, offering a numerical aperture of 0.9. This is kind of unheard of that you can take a surface where the device looks like a smidge or a mark on a glass plate, only of height 600 nanometers or so, can give you a numerical aperture that's high and focus light this tightly to the diffraction limit. Right. And again, if you zoom into this meta surface, this is made out of silicon. And if I go through if I take an SEM image, then you can see that each nanopillar, I'm going through this 0 to 2 pi phase wrap that is shown in these pictures, right? So I'm just showing you one of those zones. Okay. So these are what I would call a singlet meta lens, so which means single surface meta surfaces. And if you are familiar with optics or have worked with lenses or imaging systems, then what you would realize is that if I have a singlet, then my field of view is quite limited. And also these materials are quite dispersive. Silicon is quite dispersive. TiO2 is quite dispersive. So therefore, they are naturally going to offer you or have chromatic aberration. So they work really well at normal incidence and focus light at one wavelength really well. But if you go off wavelength or if you start going at certain angles, then the field of view is quite limited. Another issue with these meta lenses as you go to higher and higher numerical apertures could be efficiencies. So I'm going to address all 3 of these questions related to field of view efficiency and chromatic aberration in a couple of slides. Okay. So I mentioned phase control by changing the diameter, but you can do actually a lot more than that. You can do, and that's kind of what I referred to when I said metasurfaces offer multifunctional response. So if I have a nanopillar, then I can get a phase control. If you just go through simple matrix multiplication for an input linearly polarized light, then if you treat this as a wave plate and then you go through this material, then what you will realize is that this material gives me a phase shift while maintaining my linear polarization. But now instead of making this a rectangular shape, if I make a square shape, if I make it a rectangular shape or an elliptical shape with very well controlled phase along the two axes, and I choose this phase difference to be pi over 2, which basically means that along these two axes, my light is pi over 2 out of phase. So now my rectangular nanopillar acts as a quarter wave plate. Okay, if I do this for a pi phase shift between these two axes, then it acts as a half wave plate. So now what you would see if you do the math here is that if I have a quarter wave plate, then what I can do is if I have linearly polarized light coming in, then by propagating through this nanopillar that is rectangular in shape, I can simultaneously control polarization and phase, which basically means that using a single layer optic, I can create a circular polarization light field for a linear polarized input, as well as focus light with a very, very high NA. So you can do two functions at once. Same thing with a half wave plate. A half wave plate, if you have worked in a lab, together with a linear polarizer is an amplitude modulator. Right, so you have a linearly polarized light coming in, a half wave plate rotates the linear polarization by a small amount, and then if you have a polarizer, then it will kill the light. So you can again do amplitude and phase control with a single nanopillar acting as a half wave plate. And then these are all what I call propagation phase based approaches. There's another approach which is called Panchratnam Berry phase or geometric phase approach, where now you design your nanopillar to act as a half wave plate, but instead of exciting it with a linear polarized light, you excite it with a circularly polarized light. So when you have a circular polarization coming in, what a PB phase or a geometric phase metasurface does is it rotates the handedness to opposite handedness. So if you have left circular coming in, then you will get right circular with a phase given by 2 times the rotation of this nanopillar. So rotation angle of this nanopillar, 2 times the rotation. Okay. So what is the advantage? If I'm trying to make a lens out of a PB phase approach or a geometric phase approach versus a propagation phase approach, in this approach, I necessarily have to make nanopillars that are of different sizes. Here, I just have to make a nanopillar of one size and rotate it by different amounts. Okay, so lithographically, I think this approach, geometric phase approach, is easier and more reproducible, offers higher efficiencies. Is propagation phase based approach is lower efficiencies, except the shortcoming of geometric phase approach is that you have to work with circular polarized light. Okay, so this is sort of my introduction of metasurfaces for you. Okay. In terms of material platforms, these are all SEM images of metasurfaces that we make regularly in our lab here, in our clean room here. So we work with 2 different material platforms, silicon and Tantala, when we have to work with direct dry etching. So we deposit these films using PECVD or LPCVD process, or sputtering in this case of Tantala. And then we etch them using standard dry etching recipes after E-beam lithography. And then we have also developed process for what is called Damascene lithography. And if someone of you are curious, I'll speak more on this after. I can talk more about this lithography approach after. But the Damascene approach relies on low temperature atomic layer deposition. Okay, and so here we leverage and this Damascene process or this ALD process for TiO2 and hafnia that we have developed in our lab to create again high index or high aspect ratio nanopillars. And the reason for these 4 choices is silicon works fantastically well in the near infrared to IR to all the way to terahertz frequencies, whereas TiO2 works great until visible frequencies, but needs Damascene. Tantala is very similar to TiO2, so is silicon nitride. And hafnia allows you to push the response down to deep UV. Okay, and then more recently we have developed lithography approaches on making these nanopillars on gallium arsenide and lithium niobate, and this is for non-linear metasurface applications that I'm not going to talk about in this presentation. Okay, so I mentioned the issues with efficiency, aberrations, and field of view. So there are approaches proposed in literature, including work that is being done in my group on sort of addressing some of these. So for example, if you take a nanopillar, say of square shape that I talked about before, and you make a lens out of it, and I showed you an example of that using a silicon metasurface, the typical efficiencies, at least in my lab, that we get are on the order of 50 to 60%. Okay, that's just fundamental to silicon working in near infrared and the quality of the films we get or the quality of lithography we could do. But turns out that if you change your library from a square nanopillar to something more exotic shapes, like a bunch of other shapes such as plus signs, circles, a donut shape or a plus for the circle, then just by going to this expanded library, one could really improve the efficiencies to go up to like 70 to 80%. Okay. And then finally, if you really are trying to push efficiencies up to 90%, then there's a lot of work being done in inverse design and machine learning based approaches, where now your algorithm is going to spit out a design that doesn't look very, very intuitive to you. But turns out that this approach gives you efficiency that are much, much higher than what you would get from very, very intuitive shapes like the ones I've shown here. Okay. So it just depends on what you're trying to do and what efficiency you can handle. But there are approaches in literature that can give you quite high efficiencies. Okay. Chromatic aberration is another issue. So if I take again this one of these nanopillars, then this is going to give me a very different response for different wavelengths of light. But there are again approaches proposed in literature, again by pretty much expanding the design library. So this square nanopillar or a rectangular nanopillar gives me 2 degrees of freedom, which is the 2 side lengths. Whereas if I go to 3 nanopillars placed next to each other, then I have 10 degrees of freedom. So you can kind of see that just by increasing the complexity of your unit cell, you get much bigger design freedom. And by having that design freedom of so many free parameters, you can now engineer a system to give you the response that you want. So here, by using 3 nanopillars, Federico Capasso's group again showed that they can focus light, diffraction limited at the exact same focal spot all the way across visible frequencies. Okay. Hey, but pretty much all of these functionalities come at the expense of computation. Basically, you increase your library, you have more design freedom, and therefore you can get more functionality of your system. And then finally, one word about field of view that it gets important in the application that I'm going to be speaking about is that if you focus light at a high numerical aperture optic or a singlet optic, then you will get a beautiful PSF that looks like this. But if you just tilt your illumination by around 10 degrees in a singlet surface, then what you will start seeing is this sort of coma-like aberration. Okay. But again, there are approaches proposed in literature where instead of making a metasurface only on one surface, you can make metasurface on both surfaces. Now this is a doublet, and doublet is able to offer you much higher field of view than you would get from a singlet. Okay. So again, there are solutions for each one of these problems in the literature, and it just depends on what your application and what you can handle, but everything is pointing towards getting high efficiency, high field of view, low aberrations across the entire visible frequencies using, say, inverse design approaches and a doublet based configuration. Okay. So this was kind of my spiel about optics, but the metasurface field has kind of really exploded in the last few years, from collecting light from single photons with very, very high efficiencies to coupling light into single mode fibers with, again, very high efficiencies, to nonlinear beam shaping, to quantum light generation, manipulation, and detection. Okay, so there's a beautiful review that came out, particularly on quantum light generation manipulation system, where the people have generated entangled photon pairs or hundreds of entangled photon pairs from a single metasurface. And talked about other quantum applications of metasurfaces that is in this review paper that came out last year. Okay, so that is kind of my, this is all about sort of spatial domain shaping, I will still call it, because this all has to do with generating light with well-defined phase, amplitude, and polarization, and for incoming light. But you can kind of equivalently do it for time. Time becomes a little bit more complicated because if you have a femtosecond pulse, if you work in an ultra-fast lab, then the fact that the pulse is short means that you have a lot of colors, and I already told you about the chromatic aberration issues. So what you have to do if you want to shape an ultra-fast pulse in time, then the typical approach is you use a grating and a mirror to separate out all the colors. Okay, so if I have an ultra-fast pulse and I separate out all the colors, then in the focal plane of this pulse shaper, I can create a metasurface that individually addresses these colors. Okay, but the issue is if I have a 10 femtosecond pulse, then this 10 femtosecond pulse consists of approximately 200 nanometer bandwidth, with individual comb lines that are separated by, say, the repetition rate of your laser, which is around 80 megahertz or gigahertz in some cases. So you have thousands of comb lines. So you really have to make hundreds and hundreds of metasurfaces to address these, which is kind of shown here. So if I take this metasurface that is created in my lab, it is 2 centimeters long. It has 660 different metasurfaces embedded in them. If I zoom into a small section, then you can see these individual metasurfaces. And if I zoom into one of these metasurfaces, then this is how they look like, where individual unit cells are designed to address one color. So this particular one, for example, is designed to address blue color. And then as you go further along towards this end, there is a metasurface that addresses the red end of the spectrum. And now if I have all these colors separated and I recombine it, then I can get very exotic pulse shapes out. For example, shown here is that if I have a Gaussian pulse with a linear polarization going in, then I can create a pulse where the pulse starts out linear, but it becomes circular. It changes its handedness, whereas is spatial beam shape goes from completely Gaussian to being completely to a beam that is carrying orbital angular momentum. So you can do very, very exotic pulse shaping things with a single layer metasurface that is simply not possible with say any conventional approaches out there. Okay. All right, so I'm going to, this was all my introduction about metasurfaces, and I'm going to sort of speed up a little bit here and give you a quick introduction on AMO systems, specifically clocks, and why there's a need for it, and how integrated optics addresses some of these challenges. Okay. So the question that I'm going to answer in the second half of my talk is how to move laser cooled atoms and ions out of the lab. So if you have been to an atomic physics lab, it looks quite complicated. It has multiple laser beams coming in, typically to create a magneto-optical trap, or what people are called MOTS. And over the years, I would say since like in the last 2 decades, there has been some effort in trying to create some miniaturized versions of these MOTS versions or integrated. And the idea is that if you can trap an atom, then you can do sort of a lot of very, very cool physics with it, or create a lot of different measurement platforms. So cold atoms and ions, they serve as calibration-free measurement platforms, meaning they are self-calibrated, because we know once we trap the atom, then we know its atomic levels really, really well. So you don't need to calibrate it against something else. And they're used in clocks, gyroscopes, and magnetometers. They make the best clocks, they make the best gyroscopes and magnetometers. And they're also the leading components for this new quantum revolution, meaning that single photon sources, quantum memories, atomic qubits, they're all going to be based or primarily going to be based on these atomic systems, unless you're going to sort of these solid state systems. So they are one of the candidates. So the question is, how does one simplify this to something that is low swap, manufacturable? You can go to a foundry and make it, and then people can use it and rather than having these very, very complex setups. Okay, so that's kind of what I'm going to address. And low swap here means size, weight, and power. Okay, so you're trying to make a system that is low swap. Before I go into it, I'm going to rather than going into each one of these, which is a talk in itself, I'm going to talk mostly about clocks, because that's our project. Is we are trying to make a very, very miniaturized integrated photonic based clock here at NIST using a DARPA funded project. Okay, so if I now look at, I'm just going to give you a quick introduction, 3-slide introduction on atomic clocks. So if I look at the simplified energy diagram of, say, a trapped atom or trapped ensemble of atoms, then typically when you're trying to make an atomic clock using microwave-based approaches or optical approaches, in microwave clocks, they probe the hyperfine structure of this atom, whereas in an optical atomic clock, you probe the electronic dipole transition. Okay, so the local oscillator in the optical clock is the laser, whereas the local oscillator in a microwave clock is a quartz oscillator that works as say 10 megahertz or some multiple of some carrier frequency that you're trying to probe. Okay, but if you look and market out there today, every single commercial product out there is a microwave atomic clock. There's not a single optical atomic clock in market today. Okay, and why does one want optical atomic clock? In order to understand that, one has to look at what is inside a clock. So if you go to Microsemi or Teledyne, these are like, and there are a few other companies out there, you can actually buy these miniaturized 1 centimeter by 1 centimeter or 2 centimeter by 2 centimeter atomic clocks. They work quite well. And if you open this box, there's a small optics experiment going on in there. So there's a laser, there's a quarter wave plate, there's a rubidium vapor cell, and there's a photodiode. So what you basically are measuring is this absorption transition in the rubidium vapor. So you have a microwave synthesizer, quartz oscillator, and then you probe this hyperfine structure. And then once you lock to that transition in the rubidium, say, vapor cell, then you can use that as your user output. Okay, and the performance of an optical clock, which is given by this Allen deviation, and given here, a standard deviation, is inversely proportional to Q. Q is directly proportional to your carrier frequency. So in the microwave case, this is in the gigahertz frequencies, and an SNR, which is directly related to how many atoms you are probing. Okay, so for a good atomic clock, you want high carrier frequency and low SNR. Okay. So you have high SNR, which means large number of atoms. So in the microwave atomic clock, the fundamental limit, just because of the carrier frequency, is around 10 to the minus 13th. But these atomic clocks that you buy in market, they give you a number of around 10 to the minus 10, 10 to the minus 11. They're quite well, but they're not the best atomic clocks. The best atomic clocks optical atomic clocks, which naturally are, give you a frequency accuracy of around 10 to the minus 18. So 6 to 7 orders of magnitude larger than that. Now, if I go to an optical atomic clock, you will naturally see that instead of a local oscillator being a quartz crystal oscillator, it's a laser. Laser probes the electronic transition, you lock it, and then, but the laser frequency is hundreds of terahertz, is useless. So what you do is you then, once the laser is locked to this atomic transition, you frequency convert down to an RF frequency using an optical frequency comb. Okay, so now you can see that in the optical clock, the Q is 10,000 times larger. Lasers are naturally more stable than quartz crystal oscillators. The uncertainty is smaller. So therefore, all of these things combined make optical atomic clocks much better in frequency stability than a microwave atomic clock. Okay, so really there is a push from the community, from defense, from a lot of different organizations in trying to make optical atomic clocks smaller. Okay, if I now look at the market, this is microwave atomic clock market. You can buy these ones for a few $1,000s maybe. Then if you want better frequency stability, then you can go to, say, a bigger system, and as you go to larger and larger system, the microwaves get better, but you cannot break this fundamental limit of 10 to the minus 13 per square root of tau. And if you go to the best atomic clock, which is, say, let's say in Junier's lab, and this is a strontium atomic clock showing the blue and the red colors. This gives you 10 to the minus 18, 5 orders of magnitude better, but they are mess. You cannot take this on a field. And then there was some effort done, published in this paper in Nature Physics in 2018, in trying to make a strontium atomic clock that is 4 orders of magnitude worse than the best atomic clock, but on a tractor trailer in Europe. And then they drove this tractor trailer around Europe to do geodesy measurements of the mapping the topography of the Earth. Okay, so there's some effort being done in terms of trying to push these clocks to be something that is manageable. Okay, and I'll talk about some of our effort in that area. So why does one want to make the clock smaller? So if you look at all of these clocks out there and you plot them as a function of its ADAV, which is the frequency stability, and its size, then the larger clocks are always better, as I've already shown you. So there is a trend that goes this way, and what DARPA and other agencies want us to do is to break the trend to go this way, which is make it small but maintain the performance. Okay, and all of these clocks sort of enable a number of different applications. So navigation to exploration to telecom, finance, military. There's so many applications for an atomic clock, from gyroscopes, radar, and whatnot. So there's a huge need for creating a portable optical atomic clock that works fantastically well and that is small in size and manufacturable. That is portable, you can take it to places. Okay, so that takes me to the last part of my talk, which is going to be talking about our work on creating a chip scale optical atomic clock using integrated photonics only. Okay, so if I again go back, I'll talk about some of our work on using metasurfaces to create portable atomic clock. But if I go back to this plot again, and I told you that the ADAV is inversely proportional to the carrier frequency, so optical atomic clocks is better, and signal to noise ratio is directly proportional to the square root of n. N is the number of atoms. That's why fountain clocks are fantastic, is because you can work with large beams. Okay, so you can kind of see the challenge in trying to make these optical atomic clocks smaller, and the challenge is that you want to trap a large number of atoms. You want to cool a large number of atoms. To cool a large number of atoms, you need a large beam, typically centimeter scale sizes. If you work with integrated photonics, you know that when I guide light in my waveguides, my beam is approximately hundreds of nanometers in diameter buried in the waveguide. So the challenge really is, if I use integrated photonics to trap atoms, how do I go from these hundreds of nanometer beam to something that is centimeters in size in a package that is only few inches by few inches, right? So this is quite a big challenge. And I'll show you an approach based on metasurface and integrated photonics, where we are proposing to take one of these atomic clocks, strontium atomic clock in this case, and give the same stability as this tractor trailer experiment, but in the size of a coffee cup. Okay, so this is kind of the goal of the project. And naturally, it doesn't just use metasurface-based optics. It uses photonic integrated circuits. It uses microcombs. It uses on-chip lasers. It uses reference cavities that are built on-chip. So there's a number of technologies that have been developed over the last 10, 15 years. And sort of our approach leverages all of these put together to create a very small portable atomic clock. Okay, we are not there yet. We are in the middle of the program, but in a year or so, I think we have a viable path towards creating a portable atomic clock that is the size of a coffee cup and matches the performance of this tractor trailer experiment, for example. So I'm going to be talking mostly about use of metasurfaces here, and then I'll finish by talking about indicated photonics. But if you have followed literature on metasurface, then metasurface has been used for a number of different things, but it has never been used in an atomic physics setting. And so because atoms are very, very sensitive to stray fields, so if the optical imaging or scattering performance or beam shaping performance is not ideal out of a metasurface, then atoms will heat up and leave the trap. So sort of an AMO system actually presents a very stringent test for metasurface based optics. Okay, so I'll talk about that. So what can you do? The first experiment that we did was to try to trap an atom in a very, very simple configuration called an optical lattice. So basically what you have is you have a rubidium vapor source, that is, the source is here. You bring your rubidium vapor in this cell, and then you create an optical lattice by retro-reflecting a beam. Okay, gently focusing into the cell and then retro-reflecting it back. And then what you do is you replace one of the optic with a metasurface to see if you can even trap atoms, similar to what a conventional lens would do. So basically what we have done is replaced a lens with a meta lens. This is the simplest experiment one could do. And indeed, what we saw was that when we replaced the lens with a metasurface lens shown here, then we were still able to trap atoms. Okay, and you can do sort of more rigorous characterization of the trap, look at the lifetime, number of atoms, you can look at the trap modulation frequencies, do all the math. And basically, the conclusion comes out to be is that the metasurface actually works pretty much similar to how a conventional lens would work. Okay, so that was great that this was the first demonstration of trapping an ensemble of atoms. Here, 55,000 atoms of rubidium in a 130 microkelvin deep lattice. Okay. But the real challenge is trying to not trap an ensemble of atoms using in this lattice configuration, but rather trapping single atoms. So this experiment has been ongoing for 2 years, and now I think we have data. This is still unpublished work where we mount a metasurface optic, high numerical aperture in this case, inside the science cell. This metasurface is consisted of silicon nanopillars, as you can see here, and it focuses light to a very tight spot and is able to trap single atoms and then also image them simultaneously. So that the trapping light goes into the cell, the metasurface is inside the cell, it traps atoms, single atoms, and then it can image it directly back. Not only can you trap single atoms, but you can trap an ensemble of atoms by just changing the incident angle a little bit. So this kind of goes back to this field of view question. So this particular metasurface, which is a singlet in this case, has a field of view of around 20 microns. So basically within 20 microns, we are able to trap 9 atoms. So you can now think of these 9 trapped single atoms as your qubits for your quantum computing or simulation application. Right? So this is kind of where we are going is metasurface based optic completely replace a bunch of conventional bulk optic that you would need to create such a trap. And then I'll show you a path towards directly putting this metasurface on integrated photonics chips where we can directly use integrated photonics with no free space optics, such as to create this. Same thing, you can do more rigorous characterization of this trap. You can look at trap depth, you can look at trap frequencies, you can look at the field of view, and pretty much all of these points towards that metasurface is basically working as well as a best A-sphere or microscope objective will work. So this was the first meta-lens based lattice and dipole trapping of rubidium atoms demonstrated. We are still working on the manuscript and finishing up some experiments, but this was very, very a positive feedback for us from our atomic physics collaborators that indeed a metasurface works as well as a conventional optic would work. But again, going back to this challenge of how does one go from a tractor-Taylor experiment. So trapping single atoms is one thing. It's not good for clocks. It's good for quantum computing and simulation stuff, acting as qubits. For clocks, you need large number of atoms. So how does again one create large number of atoms in a very small package? And here, of course, the clock requires a lot more things than just photonics to trap atoms, but photonics is the heart of it. So it needs lasers, it needs reference cavities, it needs combs to frequency convert down to RF that you can use for your experiment. But the primary space-taking space or embodiment in this system is your atomic trap. So how do you create a trap in a very, very small configuration? And it needs number of different lasers. So our proposal, together after a number of simulations done by our collaborators, was to use this hybrid cubic Mott geometry. So the idea is we're going to guide light in photonic integrated layers to different of these rectangles. These are extreme mode converters. I'll talk about that in a second. And then these extreme mode converters are going to interact with these metasurfaces. Metasurfaces are shown by these Lego blocks here. And then they're going to redirect and collimate and change the polarization of light in very odd ways. So this whole package is now creating addressing all of these colors is creating beams that are centimeters in size with very well-defined polarization and very well-defined angles, light going at different angles, and trapping an ensemble of atoms in a configuration that is only 1 inch by 1 inch by 1 inch. So this whole thing is 1 inch by 1 inch by 1 inch with no free space optic. Okay, so that's kind of the vision of it, and that's where we are progressing. So I'll show you some examples of this or some data from this. But the idea is that you use the blue color to trap, first do what is called the deep cooling. Then you further cool it down using the red color, which is 689. And then you create put these atoms in a lattice using 830 nanometers. And then you probe the clock transition using 698 nanometer light. And then for all of these, we need certain beam powers in our beams coming out of this PIC chip. And then we need certain polarization control. Okay, so again, you can see the power of integrated photonics here, that you can guide light and you can redirect light into different angles. And then, but the challenge still is, how does one create a centimeter scale beam, only 1 centimeter off the chip coming from a PIC? Okay, that's the challenge. So I'm going to show you two approaches. One is using a photonic integrated circuit and one is using only metasurfaces. This is sort of our low-lying risk mitigating approach, but our eventual vision is using photonic integrated circuits. Okay. So how does, again, one create these beams only using metasurface and then putting a PIC layer to create these beams again. Okay, so I'll talk about metasurface first, then I'll talk about PIC, and I'll conclude my talk. So here's a metasurface based approach. So you can see we designed a metasurface chip to give us these 6 beams, at least for the blue color. Then you have 3 more for the red color. So this chip has 12 metasurfaces. Each metasurface is shown by this block here. If you zoom in, this is how the nanopillars look like. And each metasurface actually does the function of 3 free space optics. It does the function of a mirror, tilts the light at 45 degrees. It converts linear polarization to circular polarization, and it changes the diameter of the beam from a few millimeters, in this case 2 millimeters, to a centimeter here. Okay, and so if I shoot light at 3 of these and I look at the fluorescence on a piece of paper or this glass slide, then you can kind of see that when I illuminate these 3 metasurfaces, I can generate these 3 very large beams, almost just 1 centimeter away from the chip. Okay, and this is where the trap is going to be. So the power is kind of shown in this picture, and this setup here this is our strontium dispenser. The bottom is 3 collimated beams illuminating this metasurface, and top is what a typical conventional atomic physics experiment does. So you can kind of see the stark contrast is that for the top, we need all of these optics, mechanics, everything, and the bottom, we just need this 1 semiconductor wafer, nothing else. Right, so you can kind of see the amount. If we put the same semiconductor wafer on the top, then all of these mechanics can be gone. So you can kind of see how simplified my whole system can be, how integrated everything could be, where you're just illuminating this with free space beams that are collimated coming from, say, single mode fibers. Right. Here is again shown the complexity of it. So all of these optics that are shown here with this mechanics on the top to create a strontium atomic trap that is shown in this picture here is for the top beams. Right, the bottom beam is a semiconductor chip that is sitting right at the bottom, right, that you can barely see in this science cell, right? So again, that sort of points towards this idea where you can take a single semiconductor wafer, make metasurface optics on it at well-defined location with well-defined functionalities, and completely remove all of these complexities from your optical setups, right? And that's kind of the power of metasurface. Okay, so now the next level up is this approach of using photonic integrated circuits. So this is a work in progress. So using metasurface based optics with no free space optics, we demonstrated that we can create an ensemble of strontium atoms trap. So the next step here is to put them in a red lattice, and then which is sort of the creating the trap is the most challenging part, which is done just with using metasurface based optics. So then the question is, how does one create large beams from a PIC? And the challenge is, again, as I mentioned before, I have a photonic integrated circuit made on silicon nitride waveguides. This is my silicon nitride waveguide. The mode field diameter is around 300 nanometers here or 200 nanometers here. How does one create a large beam? And that was proposed in this paper in 2008 from Vladimir Askews group here at NIST, where basically what you do is you create this silicon nitride waveguide, but you adiabatically bring this waveguide close to the slab, to a slab mode of the silicon nitride film. So when you leak light out, what you do is you slowly leak light out, and you do what is called a 1D mode expansion. So light became larger just by propagation. And then when it interacts with apatized grating and you couple light out, then that does the second dimension expansion, and you can get beautiful Gaussian beams. So you can see that in this platform that is only maybe 10 microns by 10 microns, you go from a optical beam that is in the waveguide that is hundreds of nanometer to a beam that is almost 200 microns in diameter. Okay, beautiful Gaussian coming out, linearly polarized. So these photonic integrated circuits with extreme mode converters, that's what they are referred to, were used in experiments to say stabilize laser beams in atomic physics experiments, as was done in this paper here. So again, this presents a beautiful approach of using these extreme mode converters to create large beams. But again, 100 micron is not large enough to trap large atoms. So how do you do that? Then you make a metasurface on top. So in the next lithography layer, or you separately make a metasurface and you bond it. You make a metasurface, and now you have all the advantages of a metasurface, because a metasurface cannot work with a beam that is hundreds of nanometers in diameter, but it can certainly work with a beam that is 200 microns in diameter. So what we do is then we make metasurfaces that generate these large beams because of the high numerical aperture offered by metasurfaces. So this is sort of our building block of our chip. If you look at this picture, I've only have 3 more slides left. So this is without the metasurface. We guide blue and red colors. They go to these extreme mode converter elements that are shown by these blocks here. And then in this video here, hopefully we'll show it next time, you can see that the beams are going in very well controlled directions. They intersect at the right location where we want them to intersect. We measure all of these beams. They are beautiful Gaussians of hundreds of microns in diameter coming out of this pick. And naturally, the next layer is to put metasurface on top. So this silicon wafer looking thing is my pick. And on top of it, we bond a metasurface chip that has these 12 metasurfaces. They're these small white looking dots that are hundreds of microns in diameter, and they can generate these beams. So it's kind of hard to see, but I'll plot this. This is experimental data where this chip is generating 12 free space beams coming at very well controlled directions, divergence and polarization. And they're all meeting at the center here. The ones that are going to the top are supposed to hit another metasurface chip and come back to give the correct momentum. I have another image here of, again, this pick, so you can kind of see it. This is, again, to remove some of the stray light in this experiment. We put gold layer and then created windows on it. And if I long look at the beams coming out of this pick and a metasurface combination, you can see that it does generate these really large beams that is almost 1 centimeter in height, where they meet, and they're centimeters in diameter. So it's a fantastic, I guess, platform to guide light. Picks offer a fantastic platform to guide light. Extreme mode converters give you this ability to create Gaussian beams that are collimated and hundreds of microns in diameter. And metasurfaces then give you the flexibility to change the polarization, change the directions, and change the diameter of the beam. Right. So by merging a metasurface with a pick offers you really the potential to completely replace any free space optic in your setup. Right. And then I wanted to point out this two papers that came out back to back in Nature at the end of last year. Some of you may have noticed it. This is from MIT. This is from ETH Zurich. And again, they kind of show this power of integrated photonics from a ion trap perspective. So in this case, they're trapping a single strontium ion only using integrated photonics. This is fantastic. That using silicon nitride platform on the back end, and then using either electrodes for the ion trap, they're able to trap, cool, do everything using integrated photonics, not using any single free space optics. And then the ETH group took it one step further, where they made this in a foundry platform, 10 chips in this wafer or 12 chips in this wafer. If you break out one of the chips, then they have the trap chip with a photonic layer underneath. And then the photonic layer now can do sort of multi-qubit logic gate operations, right? So when you're trying to talk to a single ion or two ions in this case, is having a beam diameter of, let's say, 20 microns or 20 microns is okay, but you can kind of see what they have to do. The silicon nitride waveguide is hundreds of nanometer. They have to do a long taper region to create this tens of microns beam. Here they do a more aggressive taper to create this tens of microns beams. But if you're trying to create a MOT out of it, then which needs centimeter scale beams, then tapering is simply not a solution, right? You really need these extreme mode converters together with metasurfaces to create these large beams. Okay, so with that, I'll conclude my talk. So I hope I've shown you that metasurfaces and photonic integrated circuits offer a foundry manufacturable approach to creating portable optical systems. And in addition to applications say in imaging, polarimetry, there are a bunch of other applications, and they offer an opportunity in integrated miniaturized alignment-free AMO systems. And the work is done by a fantastic team of postdocs here. So these are all my 5 postdocs who work in metasurface-based optics for different applications. The work is done in collaboration with Vladimir Aksiu's group here. And then our collaborators from JILA and NIST Boulder are the atomic physicists Indy Regal, Scott Papp, and William McGehee. We have funding from NIST as well as from DARPA. And I thank you for your attention and be happy to answer any questions you may have.
Thank you, sir, for such an elaborative and interesting presentation. We'll now start the question answer session. So if everyone has any question, then they can ask. They can unmute themselves and ask.
Hello.
Hey, Shankar.
Very nice talk. Very interesting.
Thank you.
A lot of cool things that you're doing. I have reasonably a basic question because I don't in this trapping business yet.
Right. Okay.
So what sort of power densities that you are looking at for these traps?
So power densities. So typical, I would say, in a single waveguide, coupling in, we are putting in tens of milliwatts of power.
Right.
And because some of these traps or ions work at blue color, 461 nanometer for strontium, silicon nitride is actually quite absorptive there, at least the films that we have. So the losses in silicon nitride is around 2 dB per centimeter at 461 on the films that we have, which are probably one of the better films out there that we get from Cornell. And so we lose quite a bit of light going through the centimeter scale propagation distances. But eventually what you need out is a milliwatt, say approximately milliwatt out of these grating out couplers. And then you lose another, I guess, 20%, 30% in metasurface optic. So the power density, I don't know the exact number, but the typical powers in the waveguide propagating is around tens of milliwatt, and coming out of the grating out couplers is a milliwatt or so.
I see. So how do you couple in then? Because if you want, such a high power being coupled in to take care of the loss, you also need a reasonably efficient way of coupling in. So
right.
Yeah.
Oh yeah. So our coupling loss is around 3 dB right now.
I see.
Right.
Okay.
So we are around 3 dB right now. Maybe can we get better? So if you saw some of the images, we do inverse taper. We are doing some metasurface based approach of coupling in.
Right.
We use tapered fibers.
Right.
And pretty much
trying everything just to reduce the loss.
You are still 3 dB. Yeah.
I see.
So,
fair enough. Another platform related question. Since your loss is a very important factor here, while you can take care of the optics with the design, I think that's quite trivial. You do suffer from losses quite a bit. I think if you
100%.
want to
100%.
Is that any
our chip loss right now, just to give you a number, is the entire loss, right? Yeah. Coming from the fiber out to the what atom see is around 12 dB currently.
Yeah.
And our target is 5 to 6 dB.
Right. I mean, it's okay for some of the other applications, but what you're looking at here, you're loss sensitive.
That's why our initial proposal was PICs with metasurfaces, which we are forging ahead with.
I see.
But that's why we only went to the metasurface based approach, because that gives us the fastest path towards creating a clock, which is needed.
You don't guide, so that's
guide, right? We just use fibers directly shoved up against the metasurface.
That's right. So is that a reason to go with silicon nitride? There are other platforms that you could exploit that will give you better loss numbers, and I believe you are not very sensitive to the size as well. I think you are already orders of magnitude small compared to whatever is out there today. But there are other platforms that could offer you much better,
Right. So that could be perhaps my guess is you're referring to either aluminum dioxide or this damascene process of TiO2 or SiO2.
Yeah, something of that kind, where your refractive index is not so bad. You are about, let's say, anywhere between 1.7 to 1.8 or 9. So that should do the job, including tantalum pentoxide or alumina. So those those will also give you similar kind of numbers, but the losses can be controlled much better from two sides. One is if you can go for some of these nitrides with very large band gap, your absorption will be reasonably low. In silicon, it's very hard to, silicon nitride, it's also very hard to achieve. And if you go from Cornell to somewhere else, it's going to be different.
Oh, exactly.
Right?
Exactly. We've gone through 4 vendors now.
That's right.
Our furnaces are terrible, so we've been jumping between furnaces.
Right. So I'm just trying to understand, is this just, availability of the platform, or is there anything fundamental that you?
So there is quite a bit of effort here in silicon nitride from a microcomb perspective, done by Karthik Srinivasan and other process engineers. Right. So there was already a know-how, but I think at the current stage we are looking at other materials. So the idea is that this extreme mode converter that I talked about, that gives you a 100 or 200 micron beam, a very small mode conversion, that requires certain index contrast in the apodized gratings and whatnot. So I guess all of that could be translated to another material platform. It's just probably a bandwidth issue.
That's a combination of factors.
Right.
Still,
and then coupling losses are still an issue. Maybe it gets solved a little bit better. Yeah, I think just going to a different material platform. I think Scott Papp Group, who is my collaborator, they are very aggressively looking at Tantala in Boulder currently, right? So, but you're right. Yeah, silicon nitride in the blue color is not fun. It works fantastically well in red color though.
Yeah. Good. Thank you.
Yeah, absolutely. Yeah.
Hi, Amit. This is Varun. I have a question on the meta lens array, right? You have it in this slide as well. Something which can be used in a camera, right? So my question is that as you start correcting the aberrations, right? Like, for example, you showed a technique to correct chromatic aberration and then coma as well with multiple layers. So things get complicated at that point, right? And one more thing is that the lenses require some air gap spacing as well for the rays to propagate to hit the surface, the right wavefronts and so on. So wouldn't the size eventually be same as the existing state-of-the-art lenses, right? Is there going to be such a dramatic improvement in or miniaturization in the lenses when compared to what is already available? What is your thought?
So my thought here is meta surface, while I don't think the size argument holds. A lot of people say that meta surfaces give you an optic that is smaller in size, but the system size does not come from component level. System size comes from free space, right? So if I make a lens, I still have to have this back focal length issue, right? I have to focus this far away. A conventional lens is going to focus this far away, and a meta lens is going to focus that far away, right? So how do you replace free space is the grand challenge, right? If you can come up with that approach, you can really shrink the system size, right? And people are now thinking about it, but at least from what you are saying, I think you're absolutely correct, right? Things get way more complicated as you add more functionality to it. So where I guess meta surfaces work really well is this sort of multifunctional domain, right? Where I can replace 3 optic with 1 optic, right? And so I can make a quarter wave plate, a lens, and a mirror, and some other element, hexagon, any phase function into a single layer optic, right? So then you replace multiple optics that work in series. I think that's one very good aspect of meta surfaces. They work really well at a single wavelength. So if you look at this system of atomic traps and atoms and atomic physics, they are great because they work at only one wavelength, right? Atoms talk to specific, very discrete wavelengths rather than a broad set of wavelengths. So in those aspects, I think meta surface is well suited for sort of an achromatic operation. My feeling is that you make a meta surface that is decent, and you do computational backend correction using sort of this computational image correction approaches that people use, like machine learning and whatnot. Right. So there are a couple of groups, say Arka Majumdar's group at University of Washington. There are a couple of other groups that basically are going that route. Is I'm not going to make a meta surface that is compact, small, and has functionality of a really nice objective that I can buy from Thor Labs or Zeiss for $20,000. That's just not possible. So I'm just going to create my PSFs, aberrated PSFs at different wavelength, and I'm just going to computationally correct it.
Correct.
Right. So I think there's some effort there. There are companies that are working on it, on computationally back-end correcting things rather than making a meta surface that does the heavy lifting for you.
Okay. Thanks.
Amit, my understanding, with this is also a comment to what Varun asked, right? For all this meta lens design, we cannot rely on this conventional method that we used to do for all these diffractive optics, unless you have a very good computational background or computational framework running behind. It's impossible to design those, I believe.
Right, but there are companies that are coming up with softwares. There is a company that we work quite closely with. It's called PlanOpSim. It's from Belgium. I think it came out of the photonic infrastructure in Belgium. And they are basically, it's a simple, very code-based RCWA simulation, and you run different combinations of it on a web server, and it spits out libraries, and you pick out which ones fit your bill, and that's all there is, right? So, but I think for all this inverse design stuff is like, it's not very intuitive, so I don't get it either.
That's right.
I don't get it either.
That's what I was getting at.
Right, yeah. But you're right, yeah. I think this sort of intuitive things are somewhat limited. Non-intuitive ones can perform well, but you really need a computer science kind of background or computational background.
Hi, Amit.
Yes.
Deepak is here. So this meta surface based this trapping of the single atom or the series of atoms which you have shown, so that this technology is like some atom specific, or we can trap any atom using this meta surface?
You can trap any atoms, yeah. So in the single atom trapping, it was done for rubidium because the goal is to try to go to Rydberg sensors approach with rubidium. You can, in the strontium trapping, we did strontium. We are working with ytterbium with a group here. You can do cesium, you can do aluminum. It's pretty much comes down to wavelengths, and some of these. If you go through the sort of the level diagram for all of these atoms, you will find that there are a couple of very atoms or ions that require UV wavelengths, like 270, one requires 310. And I guess that's where things might become challenging. Can you make a metasurface optic that performs really well and still operates down to deep UV? And I think the same is the challenge for integrated photonics, right? It's like 461, we are already struggling with silicon nitride. Right. Is there some other photonic platform that will work really well at 310 or these deep UV wavelengths? Right. I don't know the answer.
Mm-hmm. So there is no need to replace the meta surface design, which is at the bottom, like for trap.
Right. You don't need to. You may have to modify it a little bit, but the design is exactly the same. Right. There's nothing changes between atoms, right?
Mm-hmm. Thank you.
Is there any more questions? Okay, so if there are no further questions, then I'd like to thank the speaker again for his valuable time and all the attendees for the successful participation in the event. Thank you all. Thank you so much.
Thanks a lot, Arpita. Thank you, Tapa. Thank you, Varun. Thanks, Shankar. Thanks, Deepak. Bye-bye. See you all.
Thank you.
Thank you.
Bye.
Bye. Take care.
Bye.
Bye.
Bye.